Swayam Prabha. Digital India. Educated India.
Welcome back to this class. Today we'll be discussing stability of incrementally raised embankments. Last time we saw the layout and the water balance and the critical conditions for stability. This time we'll go a little more into depth into the stability of embankments. But before we start that, there was one small topic which has overflown, and that is about the decanting arrangement. Now, we talked last time that the location of the phreatic line is very important. We talked that the location of the phreatic line is very important. Keep the ponded level as low, and then the phreatic line will be low and the stability will be higher. But if the ponded level is high, you have a problem. So let's look at this. I'm just looking at the inflow. So I'm throwing in my slurry into a ring impoundment, and I want to take out the supernatant water, or the water which is at the top after the solids have settled down. So give me an arrangement. How will you do that? How will you take out the water from the top, the clear water from the top? When it's coming in, it's in the form of a slurry, and how will you take out the clear water from the top? We can have a spillway, we can have a trench, we can have something to pump it out. These are some of the options. But we don't want the phreatic line to be high. See, one of the ways I can say is, let me put an overflow weir here. Just a thought. Let me put an overflow weir here, like a spillway, and when the water level comes, I can have an energy dissipator, and I'll allow the water to overflow. But that means I'm going to allow the water to reach the crest of the spillway, right? That means I'm increasing the water level. The fact of the matter is, I could have, if at the moment my deposited slurry was at this level and the decanting, the supernatant fluid was here, I could have, so this is what the material which got deposited. Let us say this is 6 meters and this is deposited material is 2 meters, and I have half a meter of water on top. I should have removed this water. If I had removed the water, the phreatic line would have been low. But we want to operate it like a lake, so I allow the water to fill and more water to fill and more water to fill. What happens? Phreatic line rises. So I need a decanting arrangement which allows the water to come out as the ash settles and the clear water moves up. That's the criticality of design. Otherwise, I can always make a well, right? So that just like you have the overflow weir, I can make a well that when the water is at this level, it will flow into this and go out. But all these wells with water inflowing from the top, or the weirs with the water overflowing from the top, they make the water level go up. I actually need something which is moving. Moving means as the ash fills up, I allow the water to come out. When the ash rises, I move it up. Think it's possible? Let's see. How do we decant? Because decanting is critical to low phreatic line. You agree? If I can decant quickly and properly, my phreatic line will remain depressed. So pumps or siphons mounted on floating barges are often used for decanting of ponded water. You should have said, sir, I'll keep a boat. I'll have a pump and a pipe. Wherever I see water, I'll start sucking it out. Right? All you'll have to do is that the boat doesn't run aground. But even if it does run aground, you won't be lost. You can still reach the end. So in India, this is not used. In some of the developed worlds, this is used, and I'll come back to why. So what we use are basically water escape towers. These are vertical concrete wells or risers with intake ports that extend from the bottom upwards to the ash deposit. Overflow weirs have been reported sometimes in the past, but not very successful. So the biggest company which handles ash ponds and therefore a large number of slurry ponds, maybe 60, 70 slurry ponds in India, is National Thermal Power Corporation. So they tend to use this water escape towers called decant towers. And the idea is that the water is allowed to spill over the periphery of the water escape tower into the tower, and this level is adjustable with some kind of precast slabs or holes. I'll show you. If I have a well or a decant tower which has several holes, okay? Now, when I am depositing the slurry here, this hole is open. So the water will go through from here. Now the ash has reached this level. I'll close this port. I'll seal it with cement, concrete. And then I allow the slurry to deposit more, then the water is overflowing from here. So the water never comes to the top. As long as the deposited slurry level is low, the level of the well is above the deposited slurry level, but is not at the crest of the dam. So at the moment what you are seeing is that, so when was slurry had deposited up to this level, this port was open. Now the slurry has deposited up to this level, this port is open, these are all closed. So the supernatant water will fall through this, go into the well and go through the dam out. And when the slurry level rises, this port will be closed. When the next embankment will be made, then the ports will go higher and higher. When the third embankment will be made, what will happen? It will sit on top of the well. So your well has to be sufficiently back in your design. If you are going to have 6 raisings, you can't have a well which comes under the footprint of the perimeter embankment after the second raising. And that was something also which was developed from time to time as we went along. So this is the concept of a barge with a pump, that you have a barge which floats around, you have a pump which sucks out the water, and it goes out through a pipe. The difference between the two is this requires no electricity. Water flows through gravity. This requires electricity. It requires power. It requires a human being to be around to operate it, operate the barge and operate the pump. Whereas here, you can open a port and go away and come back. You know that the slurry level is going to rise after 2 days or 3 days of a week or month. Then you come back and close it and open the other port. So these are called fixed location decant towers. These are called mobile barges. And you can see 2 arrangements here. If this is a side hill impoundment, this is the embankment. There can be a decant tower here, inflow pipeline here. The port is open at this level and the water is flowing out. In the case of a floating barge, your inflow can be here. Water will assemble here and you can pump it out. Now I want you to focus on one aspect which we will discuss as we go along. Where are the fines getting deposited here and where are the fines getting see, there's the coarse tailings and the fine tailings, or the coarse ash and the fine ash. In this condition, where is the fine ash or fine tailings getting deposited? Here or here? Near the decant tower. The outflow zone has the fines. So remember, when you are going to raise this, you are going to have fines underneath. What's happening here? The coarse material is depositing here and the fines will come here. So the issue always is that you should have coarser material near your embankments and not finer. So wherever the decant tower is close to the embankment, that portion becomes problematic. You know, you have a ring, I just showed you a huge ring impoundment. In the ring, the decant tower was at one end. So at the other ends, there was garland inflow. So that was not a problem because this is the beach. This is called the beach and this is called the ponded area. The beach always has the coarser material. So in all the places where the inflow pipes are on the garland arrangement, they are getting a beach, they are having the coarser material. But wherever there is the well, there is the finer material. And there you have to be careful. Water is high, fines have been deposited, strength is low, material is loose. So this is the typical design of an NTPC water escape structure. Please note this is vertically exaggerated. This is a dike. It is their drawing, not mine. This dike slope looks like concrete dike. It's not. It's a soil dike or an ash dike. So it will be like that. So this first raise is starter, first raising, second raising. Okay. So they keep the water escape structure far away, and you have an access bridge to it, such that at least for 5 raisings, it does not get submerged. They don't have ports. These are hexagonal in shape, so this is one water escape structure. Okay. They have these precast slabs which can go down grooves. I'll come back. So the precast slabs are being placed. They're continuously being raised in increments. And when you put the precast slab, you send somebody in to seal the joints. So when the slurry is at this level, water is overflowing from here, then they put the first slab, then the second slab, and it keeps on going higher and higher like that. So this is the water escape structure used by NTPC, and this is the dike. So below it, the water escape pipeline is placed. These are twin structures that have been shown. So these are the precast panels which just keep on raising the weir height. So the advantages and disadvantages: decant towers are fixed in position. Water is somewhere else and the tower is somewhere else. It can happen, don't worry. Why? Water will go where it wants to go, na? Depending on the slope of how it got deposited. So barge will go after the water. Of course, unless it is marooned in one corner, in which case also you can get a light barge and pick it up and take it there. So they are fixed in position and they need regular adjustment of the port openings. They require a conduit through the embankment. Now, you know, when we teach earth and rock fill dams or earth dams, we normally say avoid a rigid element within the embankment. Why? Differential settlements are an issue. This conduit may develop a crack. If it develops a crack, the fines will go through it. And then, just like we had a photograph today morning, you didn't discuss it. Have you seen the papers? Yes. What happened? What happened? In Chennai, something happened. I don't know. All I saw was a bus had fallen into a cavity. So there's a road and the bus is traveling and suddenly there's a gaping cavity. Obviously underground something happened, whether it was a tunnel or whether it was a collapse of a sewer pipeline. Typically what happens that buried pipelines in a long-term perspective of 50 to 100 years would have some kind of problems associated with them. So we avoid it. But at the moment we are putting conduits. These are not permanent lakes. Eventually the pond will become full. After the pond will become full, the slurry won't come. There will be no water escaping. So it is not like a lake or a dam where water is escaping all the time. Decant barges, they are flexible and can be moved. There is no conduit through the base of the dam, so they look very good, but they require pumping. And thus they need power. So in India, we are still using decant towers. In the old ponds, we had overflow weirs. What is the problem with overflow weirs? As you go up by the upstream method, what happens to the overflow weir? You can make the overflow weir for the first case. Overflow weir will be like a concrete structure with water overflowing it. Now you've moved it back. Well, you can put your overflow weir back, but the overflow weir will be resting on loose deposited tailings or ash. So that will start to have differential cracking. So you can't make a rigid structure and put it on loose hydraulically deposited material. So overflow weirs are virtually out. And many a times this problem has been referred to IITs, and we have been asked, can we put a filter embankment? That means let us have a flexible system. What's a flexible system? I have a ring impoundment. And this is my embankment. Let's make this portion a porous embankment. Porous embankment means which allows drainage. Water to flow through it, does not allow the ash or the tailings to come out. And see what happens. One can always say, all right, would you like to make a porous embankment? What will you make it of? If I ask you to make a porous embankment, what would you make it of? Cross section. Very, very porous. Gravel, very good. Even you're bothered that gravel may get washed out. What's the next step? Cobbles. Let's go to cobbles. Cobbles don't get washed out. In rivers, cobbles also come down the river in the monsoons. You're aware that when the rivers come out of hills, if you stand on a bridge, in the monsoons you can hear the big, big cobbles hitting your piers. Dum, dum. You should go to a bridge which is just downstream of a mountain range, coming out into the plains. These are rolling down like a debris flow. Anyways, so we're getting diverted. So I would like to make my porous embankment of cobbles. I don't want cobbles or boulders. You have done rockfill dams. You have earth dams. You have earth cum rockfill dams, and you have rockfill dams. Heard about them? Anyways, read up about them. These are dams which allow water to go through them, over them, but they are made of rockfill. So, sounds good? Now, what's the problem? If you make it of cobbles, your ash slurry will also come out of it. And what else? Mine tailings will also come out of it because you'll have large, large holes in it. So, what will you do? You will now make a filter. The material which is coming is ash slurry, fines. What is the fines? What is the grain size distribution of? No, total material is silty sand. Towards the inflow is here, outflow is here. What's the material coming in? More silt. So you need a filter between a silt and cobble. Oh, that's a lot of filters. Immediately, how many number of filters do you think you would like to put? Behind the cobble will be gravel. Behind the gravel will be coarse sand. Behind the coarse sand will be fine sand. Behind the fine sand will be silt. So at least 4 layers. You'll have to apply the filter criteria of the Zagi. We all aware of that, D15 and D85 ratios, the 2 ones. So basically what you're going to do then is to put layers. Looks good? Should work? Better than your well. You don't have to wake up in the middle of the night and say, oh, I had to close this port. Because if you forget to close the port, what will happen? Fines will come, and the next morning, knock, 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 Central Pollution Control Board, people will be at your office and say, here, look, white water coming, ashy water. You say, I was sleeping. So that is not an explanation, and if it is America, you'll be behind bars. Yeah, in America, they punish you for all the wrong, and therefore you do all things right. Here we say, all right, koi baat nahi, 6 ghante ka penalty le lo. Abhi hum jaake port, we are closing the port. Anyway, so I have now gravel, coarse sand. I'm just putting, please, I don't know whether this is. Assuming that I'm trying to stop fine silt from coming in, I just put silt and then your slurry will come in here. Looks very exciting. This is the solution which we should have. There are 2 problems here. One problem is, what is the upstream slope now made of? What is this upstream slope made of? What is the problem with silt? Firstly, you don't get pure silt. Secondly, erosion again starts to give you dust. it starts to get wind gullies. So you come to a designer like Manoj Datta and he will say, okay, let's stop this dusting from taking place. Let's make yet another filter. Sand, gravel. How do you like it? Any problems? This is the correct way of having an upstream slope which does not erode and still has a silt barrier inside which will not allow the fine particles to go through it. Does it look sensible or no? It's very expensive now. The expenses are going up. Anybody would like to punch a hole through this? So that's my slurry carrying the fines. The coarse particles have all settled. So what will happen? These fines will start to come in. They can't pass through, water will pass through and fines will not pass through. Agreed? Is it a good filter? Absolutely, absolutely. Once your fines start to settle, it will start to clog up your drain. You must have the capacity that what is inflowing must flow out, otherwise the water level will rise. So suppose it chokes it, you will say, so what? At least the fines are not going up. Then your water level is rising, and finally what will happen? Water will start flowing over from the top, and again the fines will come out. So flexible filters have not really worked. We've tried it at 2 locations. They worked for a few years and then they started to choke. And now let's go back to the bag filter, where we are using bag filters to entrap fly ash. You know, you have electrostatic precipitators, or you can also have bag filters for fine dust collection in various. What happens to a bag filter? In a bag filter, through the geotextile, the dust plus air goes through and dust settles and entraps in the bag filter. After some time the bag gets choked. Then what do? We can replace it or we can unchoke it. How do you unchoke it? Well, either you backflush or you take some kind of mechanical devices and bang up the bags or vibrate the bags so that if there is any material which has formed a thin film on it, it falls down. So you have to have a mechanism for unchoking. Where is my choking occurring here? Is it occurring at this gravel, sand or silt or fine sand? Or what is getting choked? Where are the fines? Where is a layer of fines formed? No. The fine silt comes and is held by the silt here. This silt. It will allow the water particles to go through, but it will not allow the fine silt part. So the fine silt particles come and form a thin film on the silt. Can I unchoke it? We don't have an arrangement. However, if instead of all this I was to make this whole arrangement but have a geotextile filter, if I was to have a geotextile filter, then I could replace the geotextile filter. That's what we are doing in a bag filter. The only thing is that the geotextile filter is progressively getting buried in the slurry which is deposited. Can you see the engineering here? You can come and say, sir, I don't agree with you. I will have cobbles, I'll have gravel, I will have coarse sand, I'll have fine sand. Instead of the silt, I'll put a geotextile filter. Right? And I will give you a geotextile filter which can remain exposed for the 5 years. Or if you are bothered about it, okay, on the geotextile filter you put some cobbles so that your geotextile filter is protected from animals, from man, from vandalizing. Right? So your silt particles will now come and sit on front of the geotextile filter. Now you want to replace it. Now you know it's not working, you want to replace it. The problem is it gets buried because the ash level or the tailings level is rising. So we need to have a chamber which is so designed where this filter can be changed with time. And so far it's not been developed. So if any of you want to do it, you can always make a design, you can patent it, you can have a startup, and you can make millions of dollars. Does it excite you? Great. I hope one of you will do this. But it's all there. Conceptually, it is possible, it is doable, but just a filter embankment does not work. So what is this diagram which I have put here? I said cobbles, gravel, coarse sand, fine sand. And on top of that, there is a dash, dash, dash line. That is what you are going to develop. That's your patented. So I've said it is a protective porous layer which will allow the water to go through but keep the fine ash in position. However, you also have to have a mechanism by which this can be replaced periodically. And this is better than all the other water treatment techniques which are being used, which is what? If you want to remove a lot of fine suspended solids in water treatment, how do you remove them? No. Your drinking water plant. You picked up water from the river, total suspended solids are high. What will you do? Sedimentation, you'll have to make a lake. Rapid sand filter. Rapid sand filter catches the suspended solids or catches something else? Everything. And what happens to rapid sand filter after a month? And what do you do to that? And then